during World War II. And we have to have a ruler to measure anything, some kind of a maßstab, and that is what I measure against. So what I'm going to try to entertain you with today is to compare what Heisenberg did with what is in here. It's actually, how many people in the room have actually read this? It's entertaining. It's, if you know a little bit about a little statistical physics or diffusion theory, if you're a chemical physicist, it's not difficult reading, it's quite easy. It's what Serber, that's why I asked the question, it's what Serber used as the introduction to get newcomers started working on the bomb. Everybody had to take this course, and it's the theory of how the bomb works. And it's this, so it's not the actual making of the bomb, which is a difficult engineering problem. It's, or the making of a reactor, which is more difficult engineering problem, perhaps. It's the underlying theory that you start with to orient yourself. And the question that has been floating around for a long time now is, did Heisenberg actually know anything, or did he not? How much did he know? And this guy on over here is Robert Serber. He is the one. He was Oppenheimer's right-hand man, a close friend, confidant. He's the one who put together the primer, which primer, we use that in English. A primer is a first grade book. It's the first grade, first year in school. You get a primer to try to learn to read. So that's how they were supposed to learn what the bomb is about. Okay. Next slide. Am I blocking anyone here?
Just camera.
Yeah. Okay. So the title of my talk is what it's supposed to be what Heisenberg did at Farm Hall, but you cannot really appreciate what he did at Farm Hall in the correct context unless you know already what he did in 1939, about 4 years before the primer came out. So everybody knows that it took, after they heard about Hiroshima and Nagasaki, it took Heisenberg about 8 days with nothing there, absolutely nothing. He couldn't bring any material with him, even if he'd had it, to work out the answer that his other 9 colleagues asked. How did they do it? How did they design the bomb? How did they make it? And he presented this in his lecture at the end of Hoffman's book. It's at the end of near the end of the Farm Hall report. And when I first read about it, I learned the primer first, which is easy, and then I went through Heisenberg's Farm Hall lecture, through the discussions, and his lecture is of course embedded in his conversations with his colleagues. It's not something separate. They're talking back and forth. He's asking questions, they're asking questions, and answers are coming. And so what I'm going to show you is that what he did was not to rediscover Robert Serber's solution. He already had the solution in 1939 in the context of the reactor. That's why we have to know what Serber did in order to appreciate what Heisenberg did. Next one. So Heisenberg was actually the first to calculate the critical radius. He had the critical radius formula in 1939. He calculated numbers for a reactor. The difficulty was getting a certain length right, because in a reactor, as opposed to a bomb, you have a mixture. You've got moderator and uranium, and maybe it's somewhere 235, hopefully a little bit more 235 than 0.7%. And so you've got three components that you have to take into account with different amounts and different cross sections. And so when he estimated the critical radius in 39, he had a method of doing that based on his earlier discussion in the G39 paper, Geheim 1939, classified 1939 paper to Army Ordnance, the Heereswaffenamt. Peierls also worked out the diffusion theory in 1939, but it has the wrong diffusion coefficient, and it's in a limit that's more applicable to a reactor, if at all, because it requires the neutron production per collision to be close to one, close to unity, not much above unity. In a bomb, you have 2 to 3 neutrons. If you have fast fission, you have 2 to 3 neutrons per fission coming out, whereas in a reactor, it's mainly U-238. And when you count the neutrons coming out, you got a number that's closer, as Heisenberg pointed out in this report, to 1.18. And they got the diffusion coefficient wrong. Serber, in 1943, reproduced Heisenberg's formula and plugged in numbers for the bomb independently, parallel, independent discoveries of the same equation using the same method, same identical method, same partial differential equation, different solutions, but I'll point out to you why that didn't matter. Heisenberg initially used a solution appropriate for a reactor, and there's a reason why the solution for the reactor and the solution for the bomb are exactly the same at criticality. Not the solution, but the prediction of the critical radius. All right. Heisenberg again at 1945 calculated using the same solution that Serber did. And, but what he didn't know, his numbers were not in agreement with Serber's for the transport mean free path, or the transport cross section, but they were close enough that you couldn't argue too much about it. They were a little bit off. He didn't know the fast fission cross section. That's the only thing he didn't know accurately. And it's not clear to me, I don't know the history of it, but I don't know when the Germans first came up with a fast fission cross section, but it had to be before 1945. He made this guess between 1/2 and 2.5 barn, right?
Yes, extrapolation.
At Farm Hall.
Oh. He calculated it by extrapolation from geometrical cross-section and that sort of stuff.
Well, at Farm Hall, he said he recalled 1/2 barn from someone's data.
That is 238.
2.5 is the geometric cross section.
That is a cross section of 238 for fast newtons.
Yeah. Okay, then that's what he used.
238.
Yeah. Okay, so the point of what I'm going to go through is that if you want to formulate criticality for a reactor and a bomb, if the reactor and the bomb have the same shape, for example, a sphere, and he did make spherical reactors, then the theory is the same. Well, the contents are the different, but the basic theory that you start with and calculate is the same. Next slide. Okay, so the history is that the Manhattan Project was motivated at least in part because of uncertainty what was happening here. They had no intelligence, it seems that there was no intelligence from either side that told what the others were doing. And so Los Alamos, Oak Ridge, and Hanford, Washington were constructed pretty quickly in 1943. That was Grove's, those were Grove's projects. And what I think is that our side would have been much more worried if they knew how much Heisenberg actually knew already in 1939. Not that it led anywhere, but if they knew how much he actually understood. Next. So these are the 10 Germans who were quartered at Farm Hall with vacation-like in a vacation-like setting. They were picked up, of course, near here. That's why we're here today. Some of them were somewhere elsewhere, I suppose. And at Farm Hall, they were bugged. How many people have read the Farm Hall protocols? So many people are not familiar. All right, they were, the point of taking them there was that they were bugged. There were hidden microphones that apparently they didn't discover, or if they discovered them, they never said it. And so they wanted to find out, the Allies, the English and Americans, French were excluded already. The Americans and French wanted to find out how much these guys knew about reactor and bomb construction. So they wanted to listen to their conversations, and they were recorded. And what was interesting is that after Hiroshima and Nagasaki, the 10 finally realized that a nuclear weapon had been constructed and used, and the other 9 asked Heisenberg, how is it possible? We thought we were ahead in reactor research. How did they construct a bomb? How could they do it? And what he did was to go away to work it out for 8 days, and came back and left and gave a lecture, which is embedded in their conversations, which you can read in Herr Hoffmann's book. So next slide. Yeah, just a comment from my side. I mean, what's obvious when you read the Farm Hall report is that there were, about four separate reactor programs here where they tended not to cooperate with each other. And in the US, there was a single unified effort where information was shared. And this is the reason it got done so fast, one reason it got done so fast there. They were told in the news incorrectly that the Nagasaki bomb, which was plutonium, was 4 kilograms. It was actually 6 kilograms, and people have wondered, did that influence what Heisenberg did in order to present his lecture? And the answer is it couldn't, because there's no room for fudging in the critical radius formula. There's nothing there, but there's nothing there but measurable quantities. There's no fudge factor. Next slide. So the formulation of the problem, the basic problem, the elementary problem, elementary theory of a bomb, you can read either in the Los Alamos Primer, Heisenberg's 1939 paper, or his 1945 lecture. It's all the same. Same partial differential equation. Different solution in 1939, but I'll explain why it doesn't matter. So what you basically start with, you've got you have with a reactor. This is all in the context of a reactor, which is not in the primer. So there's a neutron source at the center of the ball of mainly U-238, a little bit of U-235. And you shoot in these neutrons, and if you reach criticality, then you get the chain reaction, and the neutron density becomes constant. So the point is that the time dependence is exponential, and then there's a spatial part, and if this parameter lambda, if it's less than 0, the reaction fizzles. If it's equal to 0, that's the critical point. That's the point where you want to try to tune a reactor to operate. And the equation that it comes from is simply, Heisenberg actually didn't explain it, just wrote it. He didn't take these steps. He simply wrote down the equation, but Server derived it. It's the continuity equation with creation, neutron creation and destruction terms on the right-hand side. This nu is the number of neutrons that come out of one fission, which is either 2 or 3, and the -1 over minus n over t is the fact that you lose 1 neutron every time there's a fission, right? So what you have to have is nu greater than 1. In a reactor, it's close to 1. In a bomb, it's with fast fission, it's 2 to 3 per fission, where you have either U-235 or plutonium. And what's important for Heisenberg in 1939 is the neutron current. It's which he describes by diffusion. So that's the standard diffusion since Einstein, diffusion current since Einstein and Smolakowski. Next slide. You get, Heisenberg begins with this equation, with the time dependence, but he begins with this equation. He doesn't go through the derivation, he just writes it down. He did the derivation mentally. And what you get out here, of course, this has units of 1 over centimeters squared, and this has units of centimeters squared per second. That has units of seconds. And so if you divide that by this quantity and then set lambda equal to 0, which means you're working at criticality, you get what's called the diffusion, the square of the diffusion length. The number has units of centimeters squared. That's what's important. The stationary state will be critical whenever you choose a boundary condition that gives you the critical radius. It's the boundary condition that's of interest in this. So you have an equation, you've got a solution. The size of the blob of uranium in the reactor or the bomb is arbitrary, and when you choose that radius to be fixed by the so-called boundary condition, then you get the critical size for L squared. Next. So there are 2 different classes of solution for that equation. The basic solution is called the green function, technically. And it allows you, if you use that, you're assuming an external neutron source. So that's the solution for the reactor. And that's what Heisenberg used in 1939. Right? The regular solution, in the regular solution, there's no external neutron source. It doesn't describe a source of neutrons. How do you know you've got a neutron source? There's a current. If you think of a little sphere around the center of the reactor, there's a current coming out of it. In a bomb, you don't have that. You have a current coming out because of the external neutron source, even if you're not at criticality. In a bomb, you don't have that. There's no neutron source. So the main point is that the formula for the critical radius, R sub c, Heisenberg just calls it R in his papers, is proportional to the diffusion length. It's less, that is less than the transport mean free path. The transport mean free path is in kinetic theory, the average distance that a neutron travels between collisions with uranium nuclei. And in most of these, it just bounces off occasionally it causes fission, but in most of the time it's just bouncing off. So there are two so-called mean-free paths. There's the transport mean-free path and the fission mean-free path, which is shorter. And the important thing is that the critical radius, of course, the dimensions are determined by the diffusion length. They will have dimensions of centimeters. The prefactor that goes in front of L1 is determined by the boundary condition. If you choose a good boundary condition, you'll prevent loss of neutrons. If you choose a bad boundary condition, more neutrons will escape and they won't come back. This is the point of it. Next slide. So, I apologize for equations, but I have to write a few. So what Heisenberg used is the solution with the neutron source at the center. And what you'll notice about this is that if you set, so R, capital R is the radius of this blob of uranium in the reactor. Little r is how far out in the blob you are from the center. And if you set r equal to 0, n is infinite, because it goes like 1 over r. That solution is not the one you use to describe a bomb, but this is the one you use to describe a reactor, because that behavior gives you a current of neutrons coming out of the center. And this J, so there's the current density. You integrate it over the sphere, or the surface of the sphere, and he calculated the current that's coming out of the neutron source. Right? And then he was always interested in the increase, in German, Vermehrung, at the boundary. And he didn't calculate that at this stage in his Time 39 paper, G39. What he calculated was the ratio of the current, J prime, the ratio of the current at the boundary to the current of the source. And it's, if you choose the boundary condition that's very inefficient, that corresponds to air outside, no reflector, just neutrons going out into air that never come back, losing all the neutrons at the boundary, that hit the boundary, then the boundary condition is that the critical radius is pi times the diffusion length. And when you pick that, the numerator is 0, and that's why they were always looking for infinite Vermehrung in their experiments. Right? So it's literally infinite. And what he wrote next in G39 has a mistake in it. And I'm not sure whether it was intentional or whether he really made a mistake, because later in the paper, he doesn't make it a second time. He has 2 chances to make the same mistake. He makes it here, and when he goes below and adds a reflector, he doesn't make the same mistake. So next slide. So what he notices, what he says is that this ratio, the Vermehrung, is infinite at the critical point. And then he wrote that, he followed it with this sentence, wenn sich dem Wert PL nähert, so strebt J prime gegen unendlich, which is not correct. J prime is always finite. I wrote an expression for it here. It's not infinite. What happens is that the source at the origin is 0, which at first sight seems strange, but what happens, he didn't calculate this, I calculated it. What happens is that at criticality, fission, running in the wrong direction, cancels the neutron source. So the solution, that's the reason that the solution for the reactor, the formula is the same as the formula for a bomb. For a bomb, there's no neutron source. For a reactor, it's canceled. And so if you calculate leaving out the source, you get the same answer, which was Server's 1943 and Heisenberg's 1945 solution. So he inadvertently, it seems, had a prediction for the critical radius of a bomb, but never put any numbers in for a bomb. I don't know if they knew anything, what they knew about fast fission at that point, probably nothing. This is 1939. Okay. So, now what he did next in the paper was what actually Serber in the Los Alamos primer started with the same solution. He didn't talk about the current coming out because he was talking about a bomb, not a reactor with a neutron source. But they both calculated for what's called a tamper. But in English we call it a tamper, you call it a reflector, it's a neutron reflector. The idea is to surround uranium with a thick material that doesn't absorb and reflects neutrons back in. Next slide. So when you do that, and you calculate the neutron current escaping at the boundary, it's down by about a third over what it would be if you don't have anything surrounding uranium, mainly U-235. It's down by about 30%, factor 1/5. And again, at criticality, fission cancels the neutron source at the origin. So that surprised me when I saw it, and so I calculated further, and if you calculate using what's called a Taylor expansion near the origin, you will find out to about 1/6 of the critical radius, there is basically no contribution to the fission. It's from the outer 2/3. And it doesn't matter whether you're talking about a reactor or a bomb, it's all the same. Because the neutron source is not there at criticality. And then he shows with the next sentence, he added that with U-235, it would be much better than uranium. It would be better than natural uranium if you had the uranium enriched by 235. And it points out that for an enrichment of about 30, he claims that for enrichment of about 30%, a small ball of about 8 centimeters radius would go critical. I haven't gone through that. I think the number sounds a bit small. But he shows he's calculated, the point is he's calculating critical radii in 1939. Next one. So what happened at Farm Hall is easy to state. Heisenberg in 8 days, without any, he had to recall, he used here, he should preface it with this statement. I want to calculate the U-235 bomb using the method that we used for the reactor. And he means in 1939. And there it turns out that one can understand all these details of the bomb very good using our reactor theory, which is absolutely correct. It's the same theory. Different contents when you plug into it, but the theory is exactly the same. And I'm not German, but when I read it, it sounded to me like maybe he's surprised and pleased that the theory works, indicating that he didn't work it out before. There's no evidence that he worked out this solution earlier. All he did was to take away the singularity at the origin. Nothing happened, nothing special happens in the solution at the origin. There's no external neutron source, but you get exactly the same prediction of critical radius. And again, it's for a tamper. The reason it's for a tamper, for a reflector, is because instead of having pi, you've got pi/2. And that's what reduces the current by about a third at the boundary. Next. So in these discussions at Farm Hall, he says, tell me the cross section and I can tell you the mean free path. And this is important because now he's going to tell us how he calculated the numbers at Farm Hall. You start with a very simple equation which is dimensionally correct. Actually, if you were just using dimensional analysis, that's what you'd write down. It says mean free path times cross section times uranium atom density, that's little n, equals 1. It's a dimensionally correct equation. The atom density for uranium is 5 times 10 to the 22 per cubic centimeter. He should have gotten that the mean free path is 20 over sigma. He got 22 over sigma. I don't know how he got that, but Heisenberg was reported not to be very good at arithmetic. I said, I don't know what he used for n, but anyway, it's close enough. So we're going to use 22 here. And then this sigma, that's the cross section, that should be expressed in units of 10 to the minus 24 centimeters squared, which is called 1 barn, and following both Heisenberg and Sterber, we leave off the units. You just imagine that it's got units of 10 to the minus 24 centimeters squared. So what he gets for the diffusion length, remember the critical radius is pi over 2 times the diffusion length, is he gets 6.2 centimeters divided by the fission cross section. And that gives a prediction of the critical radius of 9.7 centimeters divided by the fission cross section. And to arrive at this, you have to calculate the same as Sterber did in the primer. There are no two ways to get there. It's straightforward. All right. So just to show you what the equation looks like, you can use some relationships in kinetic theory, and if you want to know what it looks like in terms of cross sections, the square of the diffusion length looks like the transport mean square path, which is capital L squared, divided by 3. That comes from the fact that you have isotropic diffusion, times nu minus 1, which is the net number of neutrons for fission. Right? Taking minus 1 takes out the one that hit the uranium nucleus, and 2 or 3 come out. And this nu is about 2.5. And this is the ratio of the transport cross section divided by the fission cross section. Next slide, please. When I first went through Heisenberg's arithmetic, I'm not very good at arithmetic. When I first went through it, I got numbers that were bigger than the ones that I have here. But when I calculated last week, you can check me, I may still make a mistake. What I got was 4.3 instead of 6.2, and 6.7 instead of 9.7, which makes Heisenberg's prediction better than it sounded at Farm Hall. Right, so he made about a 30% arithmetic mistake here. Using, next slide, using these numbers. Now this is nice because it compares what Robert Serber used in 1943 and what Heisenberg used in 1945. Heisenberg's only uncertainty is what is the fast fission cross section. Fast fission cross section. He's got 6 instead of 4 for the transport. It should be transport cross section. That's close enough, right? It's not, so Serber knew it better, but Heisenberg said 6. And for the transport mean free path, he's got 3.7 instead of 5. His biggest problem is with, his only real problem is with the fission mean free path. He says it's between 0.5 and 2.5. And if someone had told him, well, you don't know exactly what it is, you've got to decide you've got to make a bomb anyway, which no one did fortunately. He could have said, okay, I'll take halfway between the two, and that was Server's number, 1.5. So this shows you where he was off, where he was pretty close. And there's not really any reason anymore for confusion about what Heisenberg knew. It's only necessary to read his 2 papers, work through the math, work through the numbers, and that's, so the point is that if he had wanted to design a bomb in 1939, he damn well could have done it. He knew enough. He didn't know the fast fission cross section. That's what was missing. Next slide. Not quite. I want to hit the aftermath.
Okay.
And the aftermath, this is, the big discussions began in the 1990s because the Farm Hall protocols were declassified in 1992. Farm Hall was declassified in 1992, and G39 was available in 1972. It was given back to the German government. So Mr. Logan, Mr. Serber, and Hans Peter could have read it, but they didn't. So Logan and Serber wrote, Heisenberg, after a week after the jolting lesson in critical mass provided by Hiroshima, revised his first ill-conceived estimate, his back-of-the-envelope estimate, and presented a more elaborate calculation which placed the critical mass at tens of kilograms. Well, he's being unkind here. He placed it less than 10. His lecture at Farm Hall on the 14th of August, however, was a primitive, unsophisticated treatment of the subject. Blah, blah, blah. Mr. Serber was about 88 years old when he wrote that. I don't think he would have written that if he had looked at the papers again. All right? Heisenberg and Serber calculations are identical, except for Heisenberg's ignorance of the fast fission cross-section. His 1945 calculation is the same, exactly the same as Serber's. Tamper and everything. Right? Hans Bethe in 2000, when he was in his high 90s, said that Heisenberg presented the theory similar to that worked out by Peierls, but I looked at Peierls' paper and it has 2 mistakes in it. It is not the same diffusion equation, and it's restricted to the reactor limit where the number of neutrons per collision is coming out as close to 1. He states that in the paper. He's got 2 parameters, alpha and beta, and he takes a certain ratio to be small, and that fixes nu minus 1 to be small. Logan, I don't know much about him, but he was shooting from the hip. Okay, that's it. Thanks for the invitation. I'm really happy to be here.
Still, I must a little contradict you in the case of the settled, because